So, as those of you who read subsection 2.1 will remember, here we're doing mathematical probability, which means a probability is a function that obeys certain rules. Right, we give probabilities to events, and events we know are subsets of a sample space omega, but this probability must obey certain rules. And what we're going to do now is state what those rules are. And they're known as axioms, the probability axioms, or the axioms of probability. So let's look at these axioms now. So here's the definition from the notes. And it goes like this. Let omega be a sample space, we know that. And a probability measure is the fancy name it's sometimes given, is a function. And you can see we give this kind of double struck P, this kind of P with all the lines doubled. You might have noticed that's also the logo on the YouTube videos, and it's even hopefully the little icon in the top of these notes, because that double struck P is the P for probability. And it gives to each event a real number, P of A, and we say that as the probability of A, and it satisfies these three rules. So let's look at these three rules. So the first rule, number one, says that the probability is a non-negative number. It's got to be bigger than or equal to 0. Obviously, we want it to be between 0 and 1, but actually we only need to state that it's bigger than 0, and we'll be able to prove later that it's less than 1. The second statement is that the probability of the entire sample set is 1. Probabilities kind of add up to 1. You'll remember that earlier we said that, omega is the event that something happens, and something has got to happen. And therefore, the event of the whole space, omega, ought to be equal to 1. That's good. And finally, there's this third axiom, which is the trickiest, but it's perhaps the most important for using later on. So it says, let A1, A2, etc. Be a sequence of events that might be a finite sequence, like just A1, A2, A3. Or it might be an infinite sequence, A1, A2, A3, A4, A5, 6, 7, 8, forever. And they're disjoint events. Remember that we said that disjoint meant they had no intersection, which means that these events can't happen at the same time. At most, one of these events can happen. And if that's true, if they're disjoint events, then the probability of their union, that is the probability that one of them happens, is equal to the sum of the individual probabilities. And again, that might be a finite union and a finite sum of probabilities, like probability of A1 union A2 equals probability A1 plus probability A2. Or it might be an infinite union and an infinite sum. And so if we have a sample space and a probability measure, they're called a probability space. It might be worth making just a little historical note about these axioms. That writing down these axioms was the point where probability went from being like a fun thing that people do to work out if they can win card games or dice games, to like genuine, real mathematics about which people prove proper theorems, and it's just as much mathematics as like number theory or geometry or analysis or something. But I also think this is surprisingly recently. So the Russian mathematician Andrei Nikolaevich Kolmogorov wrote these down in the 1930s. I'm always astonished it's so recent. It seems like a thing that should be hundreds of years old. I might briefly mention here that my PhD supervisor, his PhD supervisor, and his PhD supervisor, and his PhD supervisor was Kolmogorov. So Kolmogorov is like my academic great-grandfather or great-great-grandfather or something. But that's just me boasting. The important thing about these axioms is that everything we want to be able to prove about probability, we'll be able to just take these axioms and prove it. No use of common sense, no use of this ought to be true, but just follow those three rules, those three axioms to get what we want. And so those are those axioms. I think we should give an example of what a probability measure that obeys these rules might look like. So the example I'm going to use is our old friend the biased coin. So we'll remember that the relevant sample space here is it can land heads or it can land tails. And so to say what the probability measure is, I've got to give the probability of every event. So the probability of getting ahead with my biased coin is going to be P, where P is some number between 0 and 1. So you perhaps won't be surprised to learn that I'm going to say that the probability of getting a tail is 1 minus P. But those aren't all the events. There's also the empty set event. You perhaps won't be surprised I'm going to say the probability of that is 0. And there's the probability that something happens, or if you prefer, the probability that we get either a head or a tail. I'm going to say that's 1. Now, I claim that this probability measure that I've just written down here obeys the 3 axioms. Well, let's check the 3 axioms. So let's check the axioms. The first axiom is that all probabilities are greater than 0. Well, because we said that P is greater than 0, that's greater than 0. Because we said P is less than 1, that's greater than 0. 0 is greater than or equal to 0. 1 is greater than or equal to 0. So all events have probability A greater than or equal to 0. So we do satisfy the first axiom. The second axiom is that the probability of the whole set is equal to 1. And hey, look, the probability of the whole set is indeed equal to 1. So we obey the second axiom. And the third axiom is this trickier one about intersections. About unions and disjoint unions. Well, a disjoint union with the empty set is just a thing itself. So there's nothing interesting to say about that. And you can't have a disjoint union with the whole set because nothing's disjoint from the whole sample space. So there's actually only one interesting disjoint union going on. The only interesting disjoint union we've got going on is the disjoint union that head union tail is equal to head tail, or the whole space. No, that's a disjoint union because you can't get a head and a tail at the same time. So that union is a disjoint one, or a mutually exclusive one. So what's the probability of head plus the probability of tail? Well, the probability of head we said was P. Probability of tail we said was 1 minus P. And if you add up P and 1 minus P, you get 1. And we can compare this with the probability of head tail, or if you prefer, the probability of the whole set omega. And you can see that we said that at the beginning that was 1. That equals 1 as well. So those two things are indeed equal. So we've obeyed axiom 3, the disjoint union axiom. So we've checked that this probability measure does obey all the rules we want it to. Here's another example whilst we're doing examples. The dice rolling, again, the old favourite. So here, the sample space is 1, 2, 3, 4, 5, 6 for the 6 sides of a dice. And the probability measure here, I'm going to say is this. A with lines about it over 6. And the A with lines about it, I mean number of sample outcomes in A. So, for example, being an even number, well, let me write it down. For example, being an even number is the event 2, 4, 6. And 2, 4, 6 has 3 elements in it. So that probability will be 3 over 6, which is a fraction is equal to a half, for example. Now, I'm not going to prove here that satisfies the probability axioms because we're going to do that next week. Those of you who read subsection 2.1 will recognise this as the classical probability. A classical probability is where you have a finite number of equally likely outcomes. And here with the dice rolling, we have 6 outcomes, 1, 2, 3, 4, 5, 6, all of which are equally likely. And so the thing we've defined there is a classical probability measure. And so next week, we'll be talking a lot more about classical probability. And in particular, we'll prove that that thing really does obey the 3 axioms of probability measures. So now in the next subsection, we're going to want to talk about what we can prove following these probability axioms we've stated here.